So let me make a couple of announcements. First of all, there'll be a math club this Friday. Should be a good one. There's actually a couple of undergraduates that we have who are in mathematical sciences that did sort of mathy type internships over last summer. And so they're going to tell you they're actually involved in things that were involved in the Marine Corps and actually everything from like doing tracking systems for the military to doing multifamily housing sort of data analysis. And not only can you see what they did, but you can see maybe how to do this kind of thing. So that should be a good one. And also, as part of our review extravaganza for the final exam, we'll have the map in on Saturday, December 10th, right here in this building, and divide the rooms up into. So what this is an all-day thing where you can show up and get math help. I'll be there all day long. And so if you've got, how many of you are in another math class? Right, a number of you are. So you can get help in any of your math classes or perhaps even math and things. I would encourage you to put that on your schedule Saturday at the end of classes right before finals week. So take advantage of that as well. Okay. Questions? Okay, so what we're going to do today, we're going to talk. And so follow your book. This will be more or less based on 6-7. So when I say an inner product, in fact, in many ways, we're going to find that a dot product is actually just a special case of this animal that we're going to talk about today called an inner product. And inner product spaces are vector spaces that are equipped with these inner products. So, for example, Rn with a dot product. So let's kind of get to it. I'm going to do a lot of kind of examples and show you. And I'm going to do right. We're going to do a lot of examples so I can show you how to use this stuff. So definition. So for those of you that are interested, when I say a real vector space, of course, I mean my scalars come, my scalars come from real numbers. This can be done more generally to different fields, particularly complex numbers. And some of the things have to be tweaked ever so slightly. And so as to not muddy the water, we're just going to worry about real vector spaces now. So suppose you've got a real vector space, like for example, Rn, but we'll look at some others. An inner product is a function that I am going to note with these kind of little pointy brackets. And what this means is I can input two vectors from this fancy notation. What do I mean by this? What this means is this function, your input is two vectors and your output is a real number. So it's a way to take two vectors and get a number out of it. So write that out. Inputs, two vectors, two elements of B, and outputs a number. And not just any function. I want my function to have these nice properties. Number one. So in other words, it doesn't matter what order I put the vectors in. The product of U and V is equal to the product of V and U. Number two, I want this to be linear, actually. So, So in other words, the inner product of U and V plus W is the inner product of U and V plus the inner product of U and W. By the way, this also applies to the first coordinate as well. Anybody tell me why? So it also should be the case that but I don't really need to write the yellow part because once I know it's good in the second coordinate, it has to be good in the first coordinate. Anybody tell me why? Why does it, if it works in the second coordinate, that is, if I can split it up this way in the second coordinate, why do I get it automatically to the first coordinate? Yeah. You're close. The coordinates don't have to be equal, but it's because of this property here. It doesn't matter, right? So because, for example, this right here, I can flip around to look like this. Then I can flip it into this. Then I can take both of these and flip them back. As long as I can do this one up here. Number three, I want the inner product to play very nicely with constants. Constant comes in part UV equals where C is in R and U and V is that point. Again, let me point out that as a consequence of this, this also means because I can flip things around, I can do it that way. Everybody okay with it? And finally, I want one more groovy property, one more nice thing. When I take the inner product of a vector with itself, then that's a real number, but I don't want just any real number. I want it to be greater than or equal to 0. And I want it to be very restrictive on when it is 0. Okay. Now, if you look back to when we first talked about the dot product, this is the exact verbatim same thing, except instead of putting a dot between the two vectors, I now put them in fancy brackets, right? So this basically gives you all the rules that you have for a dot product. Now, the dot product is a special case of inner product. Inner products in general can be more exotic. And I'll give you some examples of that. But first, let me point something out here. This last property here allows us to find the length for and let me, I'm getting the cart before the horse here. Let me point out that my definition here is, this is what an inner product is. And if you have a vector space that has an inner product on it, you call it an inner product space. So if you hear the terminology inner product space, it's just vector space that happens to be equipped with some kind of inner product. Property 4 allows us to define a notion of length, and we define the length of a vector u in the square root of the inner product of u itself. Again, this is exactly what we did with the dot product. But so, for example, even in this more abstract setting, we can do things like find lengths and angles between vectors. Okay. First, simple. Yes.
So is the cross product inner product?
What's that now?
Is the cross product an inner product?
No, because the cross product's output is a vector. So any of you, so what he's talking about, if you're in Calc 3 or have had Calc 3, there's a way in Calc 3 where you can take two vectors and multiply them and get a vector. Inner products multiply two vectors, it gives you a real number. So, all right, here's the obligatory first example. So here's an inner product space. This Rn with the ordinary dot product. Here, of course, the inner product of u and v is just u dot. We already know that the dot product satisfies all four of these things, and it's got all that good stuff going on. But there's lots of ways that you can make an inner product that's a little bit different from this. Let me take this dot product and massage it a little bit. So we'll note this notation here. Okay, so suppose I have two vectors in Rn. I can define the inner product this I can define actually, well, yeah. Let me do one more thing. And let A1, A2, A3. Actually, you know what? I'm gonna do this. I'm gonna not make this general yet. I'm gonna do some more general. Let's just do it. So U is just U1, U2, and V is V1, V2. But you're gonna, it'll be easy to see it generalize. I'm going to find the product of U and V be 2 This is sort of like a scale dot product, right? Everybody agree with that? Because notice that 2 and 3 weren't there. Wouldn't it just be the dot product? Everybody agree? But now what I'm doing is I'm giving like a weight of 2 to the first product and a weight of 3 to the second one. This is actually an air product. It's different than the dot product. It gives you different results. Notice that. Let me kind of go through it a little bit. Because it doesn't matter what order you multiply the coordinates, then it's symmetric this way, right? If W is equal to W1, W2, then U, inner product of V plus W, is the inner product of U1, U2 with V plus W, V1 plus W1, V2 plus W2. And this inner product should be like 2 U1, V1 plus W1 plus 3 U2, V2 plus W. Now I can multiply these all out. And this is 2 U1 V1 plus 2 U2 or U1 W1 plus 3 U2 V2 plus 3 U2 W2. And notice that if I put this together, this is U V. And this right here is U. That's the second thing we have to satisfy. We've also got to do 3 and 4 here. So 3, so we can see this is a constant times 2 U1 V1 plus 3 U2 V2. And this is 2 CU1 V1 plus 3 CU2 V2, which is got this unit. And finally, what happens when you dot U with itself? Dot, I shouldn't say that. And the product of U with itself. This is 2 U1 U1 plus 3 U2 U2, which is 2 U1 squared plus 3 U2 squared, which is certainly greater than or equal to 0, right? Because it's 2 times the square plus 3 times the square, so there's no way that's ever negative. Notice, if U1 and U2 are both 0, then you get 0, which means that if you have the 0 vector, you get the 0 vector from the end product 0. If this equals 0, what must be true about U1 and U2? So suppose you have the following equation here. What must be true about both U1 and U2 to this equation balance? They both have to be zero. Everybody agree with that? Because if either one of them is not zero, then you've got a little positive piece at least, right? So that means that if this is zero, then both coordinates have to be zero. Everybody okay? Okay. Questions? All right, here's one that's a little bit more exciting. Here's a vector space that we've looked at several times. P of X is a polynomial. Degree less than or or the zero point. Remember this old vector space, right? What happens when you add two polynomials of degree less than or equal to n? You get a new polynomial of degree less than or equal to n from zero polynomial, right? And what happens if you take a polynomial of degree less than or equal to n, you multiply by a scalar, you still get a polynomial of degree less than or equal to n. Where's it? I am going to define an inner product this way. First, I'm going to pick some fixed real numbers. So let A0, A1, A2, AN be fixed real numbers. So I haven't specified them, but they don't vary. They're just fixed numbers. I'm going to define the inner product this way. If P of X and Q of X are in Pn, the polynomial is less than n, I'm going to find the inner product, the so for example, so let me kind of, I won't use this for except kind of examples to help you along a little bit here. So here's sort of a parallel example to help the example. If n equals 2 and A0, A1, 2, some colors and parallel. Emily, give me a number. You go 3. Okay. Even. Let's see which one answers. Give me a real number. 4. How about another 8? 5. What are you doing that? Actually, that's very interesting. Very good. So here are 3 numbers that I picked. Right? So what do I mean by this right here? So if I take the inner product, let me make up a degree 2 polynomial here. Let's look at 2 plus 3x and an inner product with 1 minus x squared. How does this inner product work? Well, what you do is you plug in the first point, both polynomials, and you multiply them. So I plug in 3 to this and I get 11. I plug in 3 to this and I get negative 8. Now I plug in 4, both these and multiply. So that's going to be 14. And this is going to be 1 minus 16. Right? And finally, I plug in pi to both of these polynomials. So this is 2 plus 3 pi, and this is 1 minus pi. And that, of course, it's a real number. I guess I can multiply it out here. That's minus 88 minus 210 plus whatever the heck this is, right? This is going to be 2 plus 3 pi minus 2 pi squared minus 2 pi. And there, that's right. Whatever that is. And now we're just extending this more. So this is a way to take a couple of polynomials from vectors and get to spit out a number. Now, is this an inner product? Well, let's kind of go through this. I won't be super detailed on this, but what do we have? We have to have this happen. Does that work here? Certainly it does, because the order of these two don't matter, right? It doesn't matter whether this is a number because I'm plugging into a polynomial. This is a number. It doesn't matter what order you multiply two numbers, right? 2 times 5 is 5 times 2. Order doesn't matter. Agree? So this thing holds up. 2. What if I add 2 poles? What happens if I do this? Well, this is just P of A0 times Q1 A0 plus Q2 A0 plus all the way up to P AN Q1 AN plus Q2 AN. Now, after having done that, what do you suppose my next step is going to be? Distribute all this crap out. And let me kind of, I'm going to keep these separate in the following sense. I get a P A0, Q1 A0. And then from the next term, I get a P A1, Q1 A1. All the way up to this one, I get P AN, Q1 AN. So now I just distributed out the first term. Now I can distribute out the second one. Q2 A0, Q2 A1, Q2 AN. And this is the unit product of P and Q1X plus the unit product of P of X. So that's it. What else has to happen? Well, I also need the constant thing to work, right? So well, if I put a C in front of this, that's the same thing as distributing that C all the way through here, which is exactly what we need here. So this is the last one is the most interesting. Right? What happens when I go the inner product of P of X with itself? This is P of A0 P of A0 plus P of A1, P of A1 plus P of AN, P of AN. Agree? Can anybody tell me why this is greater than or equal to 0? Why is that greater than or equal to 0?
Everything there squared, they're always positive.
Yes, I didn't write this in the best form possible. Exactly right. These are all squares, so it's greater than or equal to 0. It's also true, I guess, that if P is the 0 vector, that is to say P is the 0 polynomial, when you plug in all these, you get 0. So the inner product of 0 with itself should be 0. But why is it an infinite? So suppose that this actually turns out to be 0. Suppose that you have the inner product of P with itself to be 0. For this to be an inner product, the only way that that should be able to work is if P of X is the 0 polynomial. Right? Well, we'll see. We'll see about that. This one requires a little bit of thought. Okay, so I've got that. Can somebody tell me, maybe you don't know how to finish it, but can anybody tell me something that I can push forward on this? What must be true? Yes.
Well, it was if PA0 or PA1 or anything other than 0, then the magnitude is greater than 0, you add them all up.
Okay, right. So what you're concluding then is all this crap in parentheses, every one of those separate things has to be 0, correct? Everybody agree with that? So it must be true that P A0 is 0, because if it's not, then it squares some positive number, and there's no way that the rest is to be negative to bring it back down to 0. Agree? So this has to be 0. When you plug in every one of these points, those all have to be 0. How can we conclude that we need to be able to conclude P of X is the 0 polynomial, right? That it is the polynomial that is 0. How can we do that just with this information? Yes.
Well, I mean, we picked our A's to be on 0, so.
No, we didn't. We just picked them all to be different. Yeah, that's all they have to do is be different. Let me ask you this. There is a specific restriction that we do have on P of X. What's the restriction on P of X? It's degree n or less, right? Let me ask you this. If I have a polynomial of degree 10, what's the most number of roots that it can have? Do I agree with that? If I have a polynomial of degree 27, the most number of roots it can have is 27. Agreed? How many roots does P have? Notice you start counting at 0. There's n plus 1. Everybody agree with that? But P of X is a degree n or less. But any polynomial degree n or m has at most m roots. The only way that that polynomial can have more roots is than n is for it to be the zero polynomial, which actually has integer. So p of x is the zero polynomial. So it's an inner product. And that last one is a little bit trickier. Okay, any questions on that? All right, let me give you another example of an inner product. And this one actually comes up in quite a bit in engineering. How many of you have ever heard of Fourier series? Yes, especially if you're cooking computers, you might see it. If you're an electrical engineer, I'm sure you'll see it. Here's, let me sort of play this out. Let's see. Actually, I think minus one. Job easier. Okay, now I have got a big, huge vector space here. My vector space is the continuous functions whose domain is the interval from -1 to 1. Now, we have seen that this is vector space. Let me remind you a little bit. Maybe you remember back from the calculus days. What happens when you take two continuous functions and add them up? What do you get? Another continuous function. So my continuous function is my vector. What happens when you take a continuous function and you multiply it by a constant? It's still continuous, right? So my scalars are multiplied by a real number. This is a real vector space, very big. I'm going to define the following inner product. So what's left? F and G functions. So they're in C. I'm going to find the inner product of F and G be the interval from -1 to 1. Notice, I take two functions, multiply them together and integrate them, and that gives me an output. Everybody okay with that? And notice, here's another thing that you need. It's a technical thing, you can probably do it without thinking about it, but when you have the product of two continuous functions, this is a continuous function. And what I really need that for is, so it turns out, you all remember from calculus that any function that's continuous you can integrate. In fact, you don't even need to be continuous in general. There are restrictions. Continuity isn't the end all be all. So, is this an inner product? Well, notice that FG is the interval from -1 to 1, F of X, G of X. I mean, that's certainly no different, right? F of X, G of X, G of X, F of X, the same thing. Okay, so order doesn't matter. That's good. Number two, if I have F and G plus A, you know, it's funny because now we're doing fancy calculus stuff. In a certain sense, this is easier to write out than the other stuff because it's multiply. What do you suppose my next step's going to be? I've got that going on. Now what can I do? That's right. Remember, you can split up integrals if both functions are integrable, which they are. Everybody use. Which is your product got that. See? How about the third part? The third part's actually easy. I can put that inside the integral, can I? I can move constants in and out of integrals. And I am going to put my parentheses here. And this is now. Again, the fourth one about the inner product with itself being greater than or equal to 0, and the inner product with itself being 0 if and only if function 0. Let me kind of, in preparation for this, let me kind of do a side step here. Claim. Suppose capital F of X is a positive continuous function. And the integral from A to B of F of X dx is equal to 0. Anybody know what conclusion we become? So let me kind of draw a picture of this for you. F of X, you've got to draw a function here. It's got to be positive, which means it's got to be on the x-axis or above, right? And it's got to be continuous, which means that I can't ever pick up my chalk once I start somewhere. And when I find the area under the curve is 0, what are you supposed to conclude about F of X, capital F of X?
Necessarily starts to align with the ending.
Okay. It turns out it has to. Let me give you an explanation. Anybody explain why this is true? Does it seem intuitively obvious to you all that it's going to be flat? Does anybody know what the important? Well, of course, obviously, it's going to be greater than or equal. It's going to be above the x-axis to prevent negative area from canceling things out, right? What's the importance of continuity? And by the way, it doesn't need to be continuous because, for example, this function right here this function that is a horizontal line everywhere except these 2 points is certainly not the 0 function, but its integral is 0. But this function is not continuous. So what is it about continuity that makes this true? Anyone? Let's suppose that this function is not 0. Let's suppose it's not 0. I'm going to prove to you that the function is not 0, then that integral can't be 0. If the function is not 0, there is some point here, we call this in class. there's some point that's above the axis if it's not the 0 point. Everybody agree with that? Anybody agree? And I know it's above the axis because it has to be a positive function, right? Well, let me say non-negative. Now, y'all remember that delta epsilon stuff that everybody hates in Calc 1, right? Well, here's a use for it right here. Because this function is continuous, let's say at this point here, C, that it's M above the axis, right? There is some neighborhood, a little interval, where every value of the function is above M over 2. Everybody agree with that? That's the continuity right there. You can't just jump all the way down here. It has to gently go off. That's what continuous means. And so there's some little interval around this point where the function is above the axis, where it has to stay reasonably above the axis, right? So it still has to be as high as half of what it is. Everybody agree with that? Now look what happens here. The interval from A to B of capital F of x dx is greater than or equal to the interval from C minus delta to C plus delta, that is just integrated in here of f of x. Right? And the reason this is true is because the fact that this is non-negative means this interval is always greater than or equal to 0. It's always an area under a curve. It's above the axis. And this right here is greater than or equal to every value of the function in here is at least M over 2. And the length of the interval is 2 delta. So if there's even one point that's above the axis, or above the x-axis, and this is a continuous function, then that means that interval must be at least that big, which is positive, right? So this establishes the claim, f of x must be 0 if it's continuous and non-negative. This gives me enough to finish the problem. Any questions on that? You guys kind of understand the continuity argument here? There must be this little tiny hump that's above there, and the area has to be at least that big. Okay, so let's finish this off. The interval, or if you look at the inner product of f itself, this is the interval from -1 to 1 of f of x quantity squared dx. And that's clearly greater than or equal to 0 because f of x squared is a function that is never negative, right? Because every y coordinate on that thing's positive, for sure, or at least 0, I would say. Now, if f of x is 0, then the interval from -1 to 1 of f of x squared is 0. And if the interval from and if the inner product of f of itself, which is the interval from -1 to 1 of f of x squared, is equal to 0, then note that f of x squared is continuous. And the reason f of x squared is continuous is because f of x is continuous, right? The square of the thing is continuous. And non-negative. Because every y coordinate is a square, so it's non-negative. So our claim shows that if you have a positive or if you have a non-negative continuous function and its interval is 0, claim has the interval from -1 to 1 of f of x squared is 0. F of x squared is 0 at every point. So f of x is 0. So this is also an inner product. Any questions? We will continue this discussion on Friday. You will have a quiz due at 5 o'clock on Friday. It will be posted later this afternoon. Questions? All right, y'all have a good one. Stay dry, and we'll see you on Friday.